Mastering aerospace propulsion is one of the most grueling industrial filters a nation can face. Designing an airframe requires mastery over aerodynamics. Building the engine that powers it requires absolute mastery over extreme thermodynamics. In the 1980s, India launched the GTX-35VS Kaveri engine program. The objective was to provide an indigenous power plant for the HAL Tejas light combat aircraft. The scope of the research and development effort was massive. Over 3 decades, the gas turbine research establishment spent approximately $250 million. They built 9 prototypes and conducted 3,217 individual tests. This chart reveals the critical shortfall. Designed for 81 kilonewtons of wet thrust, actual output stalled at 70.5. Simultaneously, it suffered a severe weight overshoot. Against a target of 1,100 kilograms, the hardware weighed 1,235, with early prototypes peaking over 1,400. The Kaveri did not fail because of a miscalculation in its aerodynamic design. The project hit a hard physical limit in materials science, located entirely within the engine's hot section. An engine cannot be willed into existence through blueprint design alone. To achieve target thrust, a manufacturing base must be capable of conquering the extreme temperatures of the turbine core. India attempted this technological leap largely in isolation, a condition catalyzed by the 1998 Pokhran nuclear tests. In response to the tests, the international community imposed severe sanctions. This immediately cut off the Defense Research and Development Organization from Western metallurgical technology and critical testing infrastructure. The domestic infrastructure gap was severe. India possessed no facilities capable of simulating high-altitude atmospheric conditions. To validate the Kaveri prototypes, the testing process had to be outsourced to Russia, utilizing Tu-16 and Il-76 flying testbeds. These geopolitical sanctions exposed a harsh industrial reality. Without a mature domestic manufacturing ecosystem, engineering teams are incapable of bypassing a metallurgical bottleneck. To understand exactly why the Kaveri stalled, we have to look past the macro history of the program and isolate the microscopic point of failure, the high-pressure turbine blade. This schematic cross-section of a turbofan engine highlights the high-pressure turbine. This is a hostile operating environment. The ambient temperature of the ignited fuel and air mixture exceeds 1,700 degrees Celsius, while the turbine spins under a centrifugal load of 15,000 RPM. This environment is governed by turbine entry temperature, or TET. There is a direct mathematical correlation here. Higher turbine entry temperatures yield greater thermodynamic efficiency and higher raw thrust. Early Kaveri prototypes relied on standard polycrystalline alloys. At a microscopic level, these metals are composed of multiple intersecting crystal grains packed together. When subjected to the dual assault of 1,700-degree heat and massive centrifugal stress, the boundaries between these crystal grains become weak points. They stretch, deform, and crack. In metallurgy, this failure mechanism is called creep rupture. India lacked the scaled production capability for the high-purity superalloys required to survive peak TET. Without those materials, increasing the heat to reach the 81 kilonewton target would result in the physical destruction of the turbine. Eliminating creep rupture requires a specific manufacturing breakthrough, single crystal metallurgy. This process relies on directional solidification and vacuum melting. By drawing the molten superalloy through a helical crystal selector, engineers can force the metal to cool into a single unified crystal lattice structure, entirely eliminating internal grain boundaries. Because there are no internal boundaries to separate, this unified structure is highly capable of resisting centrifugal stretching and fracturing, even at 15,000 RPM. However, scaling the production of these superalloys is exceptionally difficult. The materials are brittle and must be cast perfectly free of defects or topologies like close-packed phases, a precision threshold DRDO struggled to achieve domestically. Mastering single crystal metallurgy is a non-negotiable prerequisite. Without it, a high-thrust combat engine cannot function. Even with flawless single crystal superalloys, engineers face a strict thermodynamic paradox. The physical melting point of the metal is still lower than the 1,700-degree operating environment of the turbine. To prevent the blades from liquefying, they must be actively cooled while operating inside an environment hotter than their own melting point. Looking at this cross-section of a single turbine blade, we see the internal cooling architecture. Between 1 and 3% of the cooler air from the compressor stage is bled off and routed directly into these hollow, serpentine channels inside the blade itself. This internal air escapes through micro-perforations on the exterior of the metal. This is known as film cooling, and it creates a continuous protective thermal boundary layer over the blade's surface. The final layer of defense relies on thermal barrier coatings. Highly porous ceramics, specifically yttria-stabilized zirconia, are applied directly to the metal to insulate it from the raw gas path. Executing this requires extreme micro-manufacturing precision. GTRE lacked the submicron electrical discharge machining tolerances required to drill these perforations flawlessly. The result was severe thermal inefficiency and excess weight added to compensate for the cooling flaws. Without the industrial base to execute these microscopic cooling architectures, the Kaveri engine was physically incapable of reaching 81 kilonewtons without melting its own core. Acknowledging this metallurgical gap forced a pivot in strategic planning, resulting in a bifurcated propulsion pipeline. Rather than abandoning decades of research, GTRE salvaged the core of the engine by stripping away the complex afterburner module, creating the Kaveri derivative engine. Stripped of the afterburner, the new engine operates with reduced specifications. It generates between 48 and 50 kilonewtons of dry thrust, bringing the total weight down below 1,180 kilograms. Operating as a strictly dry engine significantly reduces the peak turbine entry temperature and the corresponding extreme thermodynamic stress. This reduction in heat makes the domestic technology viable, reliable, and flightworthy. This dry derivative will power the DRDO Ghatak, an indigenous stealth unmanned combat aerial vehicle slated for flight testing in the late 2020s. The 30-year Kaveri program yielded a functional power plant, an iterative stepping stone securing the propulsion necessary for India's future unmanned stealth fleet. India's upcoming fifth-generation manned fighter, the AMCA, demands a staggering 110 to 130 kilonewtons of thrust. The domestic technology utilized in the dry Kaveri derivative cannot safely bridge an 80 kilonewton gap. To secure this power, India entered into a $7 billion strategic partnership with France to co-develop the AMCA engine alongside the aerospace manufacturer Safran. This deal ensures a